Dear students, let us continue our study in this paper, that is inorganic chemistry, where we have focused on metal pi complexes and metal clusters. And in this particular module, we shall understand what are polynuclear metal carbonyls and their structures. After studying this module, you shall be able to know about the metal cluster compounds and what are metal carbonyl cluster compounds specifically, and then you will be able to understand the structure of dinuclear and polynuclear metal carbonyls, and we will have a detailed discussion on some of these as examples. So, let us begin with knowing about metal carbonyls and these metal carbonyl complexes. A large number of mono, di and polynuclear metal carbonyls are known in the literature that you are already aware, and these are the organometallic metal complexes containing either only the carbonyl ligands or a mixture of carbonyl ligand with other ligands. Metal carbonyl complexes are useful precursors for various other organometallic compounds and are applied in organic synthesis as catalysts. The binuclear metal carbonyls, if we talk about, they are formed by elements having odd number of valence electrons, and due to the odd number of valence electrons, these complexes have tendency to dimerize and form the metal-metal bonds, where each metal-metal bond increases the electron count on the metals by 1, and this you can notice in the structures as shown here. If you look at the formula, which is CrCO6, where there are 6 carbonyl ligands, then the number of valence electrons, if we count in chromium there are 6, and because of 6 carbonyl there are 12. So, total number of electrons, the valence electrons you can count, there are 18, and the structure corresponding is this one, as you can see. From this, if we move to Mn twice CO10, then due to manganese there are 7 electrons and 5 carbonyls there are 10, and the metal there will be 1. So, total there will be 18 contribution, and the structure you can see here. Coming to the CO twice CO6, that is there are 6 carbonyl ligands and there are 2 cobalt metal. Then due to cobalt there will be 9, and 4 carbonyls there will be 8, and the metal there will be 1. So, again there is contribution of the total 18 per metal, and the structure you can see as shown here. Some more examples you can see, they are given here, where you have the iron with 4 carbonyls and the cyclopentadienyl anion, and this is the another one where you have these 2 carbonyls as the bridging ligands, and there are 2 iron here, and there is another one where these are further complex with AlEt3. Moving further, simple metal carbonyls have well defined and symmetrical shapes. Thus, hexacarbonyls, if we talk about, they are octahedral. Pentacarbonyls, if we talk about, they are trigonal bipyramidal, and tetracarbonyls, they are tetrahedral. And if we talk about the decacarbonyls, that is having 10 carbonyl ligands in them, these complexes have 2 square pyramidal groups joined by a metal-metal bond. On the other hand, bridging carbonyls possess 1 or more carbonyl ligands shared between 2 or more metal atoms in a polynuclear metal complex. And the various types of bonding modes of carbonyl ligands, if we talk about, which are present in its metal complexes, they are, as you can see here, you have the 2M with CO, where the CO becomes a bridging one, and then this is the mu CO. The next one, you have 3 metals joined to each other, and the carbonyl is then bridged to all of them. So, this is the mu 3 CO, and there is another possibility where you have the metal, the carbonyl is joined to one and then through the pi donation it is bonded to another metal, as you can see here. So, now moving to the polynuclear metal carbonyl complexes. These are the complexes of carbonyl and they consist more than 2 metal ions in them. For example, you can notice that these are the two examples shown of polynuclear metal carbonyls. One is the Fe3CO12 and the other is osmium 3CO12. That is, you are having 12 carbonyl ligands joined with 3 iron, and the structure you can see here, and out of these you can notice that these two are the bridging carbonyls, and otherwise this particular iron is joined to 3 terminal carbonyl and this particular iron is also joined to 3 terminal carbonyl, but this particular iron, the third one, is joined to 4 carbonyls. So, total there are 12 carbonyls and there are 3 iron. And looking at the structure of this OS3CO12, you can notice that there are 3 osmium metal ions and then this is further joined to total of 12 carbonyls, as you can see, and there are no bridging ligands here. The 3 osmium are directly attached and each of the osmium is further attached to 4 carbonyls. So, after having elementary idea about the dinuclear metal carbonyls and the polynuclear metal carbonyls, now let us try to understand the transition metal based dinuclear metal carbonyls in detail. Most of the mononuclear metal carbonyl complexes, they obey 18 electron rule and they are quite stable, except the vanadium hexacarbonyl, which has 17 electrons and on theoretical grounds has the ability to undergo dimerization by forming a VV bond. However, the dimerization is not favorable due to the steric regions. Few of the dimeric carbonyl complexes, if we talk about, they are CO twice CO8, that is dicobalt octacarbonyl, or you have Fe2CO9, that is diiron nonacarbonyl, or M2CO10, where M can be manganese, technetium, rhenium, and the metal-metal bond distances in these respectively are 290, 203 and 304 picometers. In the IR spectrum of dicobalt octacarbonyl in hexane, bands belonging to only terminal carbonyls are observed, whereas in the solid state IR spectrum, the bands belonging to terminal as well as the bridging carbonyl ligands are seen. And this information indicates that there is an equilibrium in the two types of structures of the complex, as you can see here, that is, in solid state it will be existing like this, where the two carbonyls are in the form of bridging ligands between the two cobalt. On the other hand, in solution they will open up and each cobalt will have 4 carbonyl ligands and the structure will be like you can see here. So, this structure which is there in solid state has the C2V symmetry, and in this case the cobalt-cobalt bond distance is 254 picometers. On the other hand, when this is in solution form, then there is D3D symmetry and the CO-CO bond distance is 270 picometers. They will be slightly longer, and this you can understand because when you have the bridging, then these two cobalts will be nearer and it will lead to a shorter bond distance between the two cobalts. Let us now take another example of a dinuclear metal carbonyl, and let us take the case of diiron nonacarbonyl, that is Fe2CO9. This molecule consists of two octahedron sharing a triangular face and containing a 3 bridging carbonyl groups. as you can see in the structure here. The coordination number of iron atom in Fe2CO9 is 7 rather than 6. And how we can understand this? Look at the structure here. Iron is joined to 3 terminal carbonyls, which are these ones, and there are 3 bridging carbonyls, and it is further joined to another iron. So, that is how it is 3 plus 3 plus 1. The coordination number of the iron atom here is 7 and not 6. So, you can notice that here each iron atom has been attached to 3 terminal carbonyl group, 3 bridging carbonyl group, and 1 another iron atom, and this is true for both the iron atoms, you can see. And if you notice, another feature is that total in this there are 3 bridging carbonyls, and there are total of 6 terminal carbonyls in this particular metal carbonyl having 2 metals. And here the iron-iron bond distance is 246 picometers, and this is again a smaller value because of the bridging ligands which is there. So, after knowing the structure of these 2 dinuclear metal carbonyls as examples, let us try to know about the polynuclear metal carbonyls. As I told you earlier, iron, ruthenium and osmium of group 8 of the periodic table, they have the tendency to form the trinuclear metal carbonyls, and they will be forming the metal carbonyls of the type M3CO12. That is, there is a dodeca carbonyl, it is 12 carbonyl as ligands joined with 3 metal. For example, Fe3CO12. This has been described by using X-ray diffraction and IR absorption studies. The iron-iron atoms in this case are linked together by a iron-iron covalent bond having bond length equal to 280 picometers. And each of the 2 iron atoms here is attached to 3 terminal carbonyl groups, as you can see here, and 2 bridging carbonyl groups. And these 2 iron atoms are attached to a third iron atom by covalent bond. The third iron atom is attached to 4 terminal carbonyl groups and no bridging carbonyl group. So, let us understand this structure again in detail. Look at the structure here. You can notice these are the 3 iron atoms, and out of these 3 iron atoms, these 2 iron atoms are having similar structure. How? Let us see. They are first of all joined with a covalent bond to each other. Furthermore, each of this iron is further attached to 3 carbonyl ligands each. So, total 6 terminal carbonyls to these 2 irons, and these 2 irons are further attached with these 2 bridging carbonyl ligands, as you can see. So, this is how they are attached, and then coming to the other type of iron here, these 2 irons are also joined to this third iron, but this iron is not joined with any bridging ligand with these earlier irons. So, this iron is attached to covalent bond with these 2 irons, and furthermore it is independently joined to these 4 terminal carbonyl ligands. And if you look at the iron-iron bond length here, it is 280 picometers. Let us consider 2 more examples, which are the dodeca carbonyl ligands with Ru3 or OH3, that is, one is Ru3CO12 and the other is OH3CO12. They have triangular planar arrangement of the 3 metal atoms which are held together by 3 metal-metal bonds, as you can notice in their structures here. And each metal atom is further attached to 4 terminal carbonyl groups and there are no bridging carbonyl groups unlike the iron case we have discussed. So, let us look at their structure in detail, which is very similar. You can notice that this, in case of this ruthenium, the Ru bond length is 2.86 to 2.91 picometer, and there are 3 ruthenium metal atoms which are joined to each other in a trigonal planar fashion with the metal bond, that is covalent bond, and further you can see each of these ruthenium is attached to 4 terminal carbonyls. So, total you have these 12 metal carbonyl as the ligands, and there are no bridging carbonyls. Similar is the case of this osmium, that is OS3 CO12 is you can notice that all the 3 osmium are in the trigonal planar fashion. And if we talk about the bond length of OS, here it is 2.87 to 2.88 picometers respectively. So, you can notice that each of the osmium is attached to the other osmium by a covalent bond, and furthermore there are 4 carbonyls on each of this osmium as the terminal carbonyl ligands. So, collectively there are 12 terminal carbonyls, and you have the structure of this particular complex. Another thing that you can notice here out of these 2 structures is the OS3 CO12 molecule has approximately the D3H symmetry. On the other hand, in the Ru3 CO12 molecule, the average Ru to CO, that is the axial bond distance, is 189 picometers, whereas the average Ru to CO equatorial bond distance is 193 picometers. So, I am sure you have now been familiar about the dinuclear as well as the polynuclear metal carbonyls with some cases, that is how to correlate the structure and identify which are the bridging ligands, which are the terminal one, and then what will be the coordination number of that metal atom. So, let us summarize what we have learned in this module. We have learned that cluster compounds, they contain metal single or multiple bonds, and they form rings or linear chains. And apart from containing sigma or pi bonds, the cluster complexes also display the delta bonds. Metal cluster compounds are formed by almost all the metal atoms, and metal clusters consisting of transition metals, they are known in very large number in literature. And these metal bonds containing complexes, they can be homonuclear, that is if they contain only one type of metal atom, or they can be heteronuclear if they consist of 2 or more than 2 types of metal atoms. And further going into it, we have studied the dinuclear metal carbonyls, which are generally found by cobalt, rhenium, manganese, technetium and iron, and we discussed some cases to understand the structure of dinuclear metal carbonyls. And talking about polynuclear metal carbonyls, as I told you, polynuclear metal carbonyls, they have more than 2 metal in them, and these are the complexes which are formed by iron, ruthenium, osmium and rhenium. So, we took the case of some polynuclear metal carbonyls and we understood their structures.